Good evening. First, I'd like to thank Joan for facilitating this talk. And also, Rob, I very much appreciated your introduction to my fairly complicated background. So without further ado, I'm going to start discussing the historical background to these stamps. It wasn't the English or the Dutch who really got started with travels to Africa from Europe. It was the Portuguese. And it was way back in the 1400s when Bartholomew Dias left Lisbon and used a small caravel boat which had lateen sails, and he hugged the coast of Africa and was able to come all the way down to the Cape of Good Hope and then on to what we now know as KwaZulu-Natal, and then he turned around and went back to Lisbon. About 10 years later, Vasco da Gama was heading to the Cape, but he was blown off course, but came back, and as you can see below, he passed the Cape of Good Hope, he went through the Mozambique Channel onto Mombasa, which brought him away from Christian lands into Muslim territory. And the Sultan of Mombasa was very kind and gave him a pilot, which allowed him to go on to Calcutta, to India. And Vasco da Gama was the first European, basically, to travel all the way to India. And this was very important because of the possibilities of trade with East India. So the Portuguese are very proud of their navigation history and exploration. And in the harbor in Lisbon, there's this magnificent monument to the people who really made these trips. And at the head is Prince Henry the Navigator, who, as you'll see in this shot, is holding a caravel, which is a small craft that has the great advantage of lateen sails. This was probably Arab technology that they took on, but the lateen sail has the great advantage that you can actually sail against the wind. And this meant people like Bartholomew Dias could enter a bay and then leave the bay. And the Portuguese, like many of these explorers, tended to place pillars and posts indicating that this was now their land. Interestingly, the Portuguese established Angola on the west coast of Africa, and then on the east coast, Mozambique, but they did not establish territory in what we now know as the Cape. And here is a stamp showing this wonderful monument at Belém in Lisbon Harbor. And this is an interesting thing. Here in this monument is an English woman. And you have to ask, well, what is an English woman doing amongst all these Portuguese sailors? Well, this is the former Princess of Lancaster. Her name was Philippa, and she became Queen of Portugal. She actually mothered Prince Henry the Navigator and actually helped him in his interest in navigation. But she's become an iconic figure, and she shows up more and more in literature now. And there's a very fine book here, Philippa of Lancaster, which discusses the whole background. But I'll go back now to show you why did this princess from England, and she was of the House of Lancaster, very powerful people. Her father was John of Gaunt, and John of Gaunt was close to being as powerful as King Richard II, but he couldn't become king, and he had his eyes on Spain, and he had married a Spanish princess. but he was trying to use an access via Portugal to get into Spain, and so he arranged a marriage for his eldest daughter, Philippa, to the King of Portugal. And it was interesting, Philippa had seen a pretty rough childhood with John of Gaunt because he had mistresses, and she was very unhappy with what she saw, and she was determined to have a really good marriage. And so it proved. And they had 6 children, and all of them are considered by the Portuguese as the illustrious generation because of the significant contributions they made to Portuguese culture. And of these children, Henry, who was the prince, dedicated his time to ship design, navigation, and the training of seamen. And later, well after his death, his exploits and his support of navigation got him the title Henry the Navigator. So here is the mausoleum for Queen Philippa and King John of Portugal. And there are a few examples of the couple holding hands in death. It implies, I think, a very good marriage. The South Africans are well aware of the Portuguese navigations, and we learnt this at school. And here is the South African stamp commemorating the arrival of Bartholomew Dias at the Cape. And what is really important to look behind him here is what's called an astrolabe. And an astrolabe was a device which allowed navigators to determine latitude. So this was very important, and that is why it's shown on the stamp. Of all people, Geoffrey Chaucer of the Canterbury Tales wrote an important treatise on how the astrolabe functions. And it was used as something of a guideline for people trying to learn how to use an astrolabe. Apparently, it could take as much as 2 years to master the use of this instrument. And also, by the way, Chaucer was friendly with Princess Philippa, and so part of her education was probably learning how to use an astrolabe. And a Muslim astrolabe is very beautifully made, and they used it not for latitude, but to learn about time, because they needed to know when it was time for prayer. So if we take a look at this, the astrolabe goes way back to the Greeks and the Persians, and it serves as a star chart and a physical model of heavenly bodies. It was important to the Muslims for determining time for prayer. And for seamen, it was very important because it allowed them to shoot the stars, the pole star, and determine local latitude. And of course, at that time, they had neither sextants or the GPS. So if we go back and take a look at Bartholomew Dias and Vasco da Gama, we can see that they made a tremendous contribution to navigation. And because Vasco da Gama's trip to India was regarded as such an epic trip, there's a very famous Portuguese work of literature called Os Lusíadas, which is about Vasco da Gama's trip to India. And it's a long poem of 10 cantos, and in it, Camões has the gods traveling with da Gama to India, so this makes it an epic. And there's a superb English translation of Camões' work called The Lusíadas, and I've read part of it, and it's all in poetry, and the translation is beautiful. And Luis Camões, who spent most of his time in India and Macau, lost his eye at the Battle of Quetta earlier in North Africa when the Portuguese were fighting the North Africans. And all the postage stamps which celebrate this master of Portuguese literature show him with his bad eye. And even in a very modern postage stamp, you can see they have him with the bad eye, but they still celebrate Camões, and I understand his work is studied in all Portuguese schools. Now, we're going to jump 300 years to the Dutch, but we have to remember the Portuguese, when they first arrived in India, became very powerful and set up very good relationships with the Indians, and trade with Portugal went on for about 150 years. But what happened was Portugal was still a small country, and they had two serious incidents. One was a massive earthquake in Lisbon, which destroyed the city. And then also they had a very ill-considered war against the Muslims in North Africa, and they lost something like 10,000 soldiers. This was enough to weaken a country who could not then compete with the powerful seagoing nations of Holland and England. So if you go to 1652, 300 years later, we discover that Jan van Riebeck, he was a high official in the Dutch East India Company, came to the Cape, the Kaap de Goede Hoop, and to establish a watering station. They weren't interested in colonizing the Cape. They just wanted to plant crops, raise cattle, and be able to look after the Indiamen, the ships going to India. And the Dutch East India Company is actually studied in many business schools. They were headquartered in Amsterdam, and the government actually gave them a monopoly to trade with the Indies. They had over 60,000 employees, and they had the power to build forts, maintain armies, make treaties with local chiefs, and they developed their own plantations and manufacturing, and traded in spices, silks, cloth, and slaves. And they were an incredibly powerful corporation. Here you can see what the headquarters in Amsterdam looked like back then. And Simon van der Stel, who was the first governor of the Cape, built this house. If you go back to the Mayflower and the Pilgrim Fathers arriving at Plymouth Rock in the cold, it was a very different situation. The people who came with the Dutch East India Company were supported by a lot of money and equipment, and the Cape was a very pleasant environment. On top of this, in France, the Huguenots had been looked after, and there was no persecution by the Catholics. But in 1688, there was a change of power, and there was the revocation of the Edict of Nantes, and there was basically massacres of the Huguenots, the Protestants, and they left in droves, and many of them went to the Cape, and they were very knowledgeable in the crafts, and they also brought their knowledge of winemaking to the Cape. So the wineries were already starting in the 1600s. And this is a place near Cape Town called Franschhoek, French Corner. And this was Huguenot territory. And here is the beautiful Dutch architecture with this triangular top. And I often wonder whether that was one of the ideas that helped to people come up with the Cape Triangle. A few of the Huguenots, only 300, went to New Amsterdam, which of course is now New York, and built a village, and they named it New Rochelle after La Rochelle in France, which was a powerful fortress for the French Huguenots. South Africa celebrates the contribution of the Huguenots, and this is a 250-year celebratory stamp. And you can see already now we're going to see the Dutch influence in South Africa, and then, of course, the British English influence South Africa. So if we look back in the 1800s, the British decided to kick out the Dutch because they didn't want Napoleon to have any control over the sea lanes to India. So that they weren't interested in colonization, and their interests were mainly strategic. But the Cape, because of its climate, fertile soil, and a very good environment for settlers, attracted people from Holland and from France and other countries, and began to develop as a colony. And what's interesting is the early postal service at the Cape, there were no post offices, and the sea captains would place the mail in a bag coated with tar, and they would even put lead around to prevent the ingress of sea air and rainwater. And then these bags were left under stones. And other captains heading, say, back to Europe would pick up these packages and take them. And I think that's where this name, the mail packet, comes from. Later, with increasing colonization and the growth of settlements, formal post offices were set up at the Cape. So this is what a postal stone looked like. And it's really interesting because, remember, the Dutch came in 1652, but here is an English captain, Cochrane, and this is 1619. And he may have been heading to India and left letters behind to be taken to England or perhaps to Holland. Now, when they started using stamps in the Cape Colony, they came from London. And there were two companies, Perkins Bacon and De La Rue, who were printing these stamps. At one time, the mail packet never arrived, and they had to print stamps in a hurry, literally within a week. And Saul Solomon, who had the Cape Argus newspaper, managed to get together two important people who basically designed and helped get out a stamp very quickly. But if we go back to the Cape Triangle as we know it, they decided not to have a fearsome Britannia with a spear, warlike. In fact, there's a reclining woman, and as I understand Minerva, it was a goddess of peace, art, and literature. And the person who actually designed the stamp was an individual called Charles Davidson Bell. And as a young man, he was producing this sort of artwork. He was recognized in the Cape as an outstanding artist. So why did they choose a triangle? This is taken out of a document. In order to obviate errors in sorting letters so stamped, we would suggest the option of a device and shape so different from the English postage stamps as to catch the eye at a glance, and we would propose a triangle with a figure of hope in the center, with the words postage, 4p, Cape of Good Hope on the surrounding border, all on an engine-turned field, as represented in the accompanying sketch by the Surveyor General Charles Davidson Bell. So he came to the Cape at the age of 17. By 35, he was the Surveyor General, but he was such a fine artist that he designed the stamp. Now, interestingly, when this artwork was sent to London, the engravers took a look at it, and they used William Humphreys, who was an Irishman, who was regarded as the finest engraver in England, to do the engraving. Humphreys had actually lived in the United States and had engraved the first George Washington stamp, which is here. So the British government had decided that it was no longer going to be distance that determined price of postage. It was a question of 1 pence for newspapers, 4 pence for a half-ounce envelope, and the Cape Colony followed this. And it was a brilliant move because it led to a tremendous increase in postal service, and business increased as a result, and countries followed this approach, requiring people to pay in advance for postage, but that often can go over any distance, and it took away a lot of the complications of charging. The Cape Triangles were interesting because they weren't perforated, so when you bought a sheet of stamps, you had to take a scissors and cut them yourself. And the value of some of these Cape Triangles is determined by the quality of the cut, where you have fine edges or where the stamp has actually been badly cut. I have a stamp where you've got some of the full stamp on one side and a bit of the other stamp cut on the other side. And this is what an envelope to England looked like with the Cape Triangulars on it. And you can see where the cuts are here. So for the talk that I'm giving, I've used two references. The one is the triangular stamps of Cape of Good Hope, which is a massive piece of work by Dr. Alan Stevenson, who was a fellow of the Royal Society, and it was published in 1950. And then a smaller book called The Cape of Good Hope Triangular Stamp and Its Story. And this was a combination of a historian, Eric Rosenthal, and a very fine philatelist, Eliza Blum, who is no relation to me. And this is a small book that I actually carry around with me because it is full of information and images of the stamps and is very portable. And again, you can see this was printed in 1957. I bought this online and it was shipped from South Africa. So why would someone who's interested in philately start studying these stamps with some very advanced equipment? Well, the company I formed some 20 years ago provides support to companies in Silicon Valley that are processing silicon wafers into computer chips. And it's crucial that throughout the production of these chips, there's no contamination. So to give you an idea, if you're not familiar with this, the wafers that are used are first sliced from a single crystal silicon boule. And historically, they started off with small wafers of 2 inches. Today, we have 12-inch wafers. And if you look inside a chamber where the wafer is being processed into chips, you can actually see they're not making one chip in the chamber at a time. There are chips all over this wafer. And once they've completed something like 200 separate steps, and that's basically putting down films and removing films and adding films to create the architecture, then they dice the wafer. And one of the terms used for computer chips is die. And this is what let me go back here. This is what a piece of equipment, it's known as a semiconductor tool, processing tool, looks like. At the far end, the wafers come in through a load lock and then come down and get processed by the robot. I'm having a problem here. The robot at the far end puts the wafer into a preheat chamber, then takes it out, sends it through to a second transfer chamber. Another robot picks it up and takes it to the process chamber where the film will be put down. You'll notice that the worker there is in what we call a bunny suit, because cleanliness is of the essence, and any particle falling on a chip can destroy it. Now, to give you an idea of what the micro world looks like compared to our macro world, I thought of looking at a Formula One racing car. This is about 5 meters long. And the machinists who work on building these cars basically use modern machine tools, but they machine to a tolerance of about 1/1000th of an inch, which in the world of Silicon Valley is 25 microns. Someone decided to build a Formula One racing car on a chip. And this is what it looks like. And here is 25 microns. They're literally building the whole Formula One within the tolerances of the machinists that build the large Formula One cars. And this is a cross-section through a memory chip that is built in layers on silicon. And this really, what we're looking at is a Model T Ford chip. But here is 25 microns. These are the individual transistors that are the switches that give you the on and off for the digital processing. And these layers are connections to the different switches and then on to actually the computer board. So if we look at clean surfaces in chip manufacture, a single particle settling on a computer chip during manufacture can destroy the chip. And if you think that it can take 200 steps and as long as 2 weeks to create a chip, contamination in these systems is really very expensive. And one of the services we provide is studying contamination when it occurred and also quality control of new surfaces coming in on parts. This requires high quality optical microscopes, a specialized electron microscope, and supporting infrared spectroscopic equipment. So the optical microscope will allow you to magnify to about 2,000 times, but after that, you need wavelengths that are much shorter than light waves, and you use an electron wave, and you can go up to 100,000 magnification. Infrared spectroscopy is used to study the molecular structure of materials. So first of all, let's look at the high-powered stereoscopic microscope. Here, Bill Damron, one of our engineers, is looking at a Cape triangular. And in the old days, we would use this microscope and take a photograph. But the modern microscope has a power drive here, and Bill can actually focus on a top surface and a lower surface. And then the system will automatically take photographs at possibly 10, 20, even 30 photo points. And so you get slices. And then the software knits it all together and you get a 3-dimensional image. And so here we can see a photo, and this is only at 25 times of the very delicate engine machine surface and the design of Lady Hope. And using this microscope, we're able to pick up fraudulent designs fairly easily. And I took this shot of Queen Elizabeth II on a different microscope, and you can see the wonderful work that the engravers have done, and even the detail in the eyes here. So when we have arrived at 1,000 to 2,000 magnification, we turn to the scanning electron microscope. And this is a system that uses an electron beam. And the beam is basically in a line here and shines, if you want, or beams onto the surface of your stamp within a vacuum chamber. And here we have an X-ray detector. When the electron beam hits the surface, it gives off X-rays, which the detector can pick up. It also projects the electrons, which are picked up as an image. So here you can see what it would look like inside the scanning electron microscope. The beam comes down like this and hits the surface. The electrons get picked up by the image detector and converted into a proper image. And the X-ray detector picks up the X-rays, and these are analyzed and can be converted into the actual composition of the surface. So this gives you an idea of just how good the electron microscope is. I just took some common and garden salt that you'd have in a salt shaker, and we magnified this to only 350 times, and yet look at the quality of that image. So when we're looking at surfaces and we see signs of stains or what we regard as possible contamination, we can use the scanning electron microscope to not only study the morphology of the particles, but also the chemistry. But this gives you an idea of what a filter cloth looks like. The thought was that this filter had been clogged, but when we magnified it, we could see that the Teflon was perfectly sound, and there was no sign of the tungsten that we were expecting. But here we're looking at 10,000 magnification. So this is the X-ray detector on the side of the electron microscope, and it's a phenomenal piece of equipment. It picks up the X-rays, and then software will convert the signals into actual chemical compositions. So here's an example. We had a HEPA filter. This is a very important filter that keeps environments very clean and should always be made of clean materials like stainless steel. And they were having problems with contamination. When we analyzed the stainless steel filter wire, which looked like this, we discovered that there was no chromium, nickel, and iron there, and molybdenum, which would be a stainless steel. Instead, it was zinc, very strong signal for zinc. And this indicated that this was nothing more than zinc-coated galvanized steel. And how it got into a HEPA filter, we don't know, but this is the power of the electron microscope in resolving issues. And a problem like this can be resolved in a couple of hours. Now, we looked at one of these wood blocks that were made in a hurry in Cape Town, and we could see that even though the wood blocks were never wonderfully done, this is a pretty poor face. And we pretty well knew that this wasn't a true, what we call a woodblock stamp. So what we did was we put this under the scanning electron microscope, and when we hit 0.1, we saw it was carbon and oxygen. This is typical of a high carbon and oxygen cellulose-based paper, so no problem there. But when we hit 0.2, we were surprised to see 6% nitrogen. Now, nitrogen is a noble gas. It's not easy to pick up in the electron microscope. This meant that the material was an amine, an amide. And the most likely story is that they used a modern polyamide ink, the sort you would get in one of your ink pens. And if you look at polyamide, this is what the molecule looks like with these nitrogen atoms. And typically, people will buy this sort of resin to make printing inks, polyamide resins. So it is interesting that this polyamide, which never existed in 1860, was being presented as an 1860 woodblock stamp. And these woodblock stamps can go for as much as $20,000. Now, we noticed under the stereoscopic microscope that Cape triangulars that we had, there was a Perkins-Bacon and a de la Rue. And the Perkins-Bacon was very diffuse, whereas the de la Rue was completely sharp. And so going to a higher magnification, and before I actually show you that, I'm going to put into your minds what happens after a storm in the desert, and you get a flood of water and you get mud, and then it dries and you get what's known as mud cracking. And this is typically what mud cracking looks like. So you know there's been a load of moisture around. When we looked at the Perkins-Bacon stamp, we discovered the surface had mud cracking. And here you can see point 1. When we analyzed point 1, it had 18% phosphorus. The mud cracking indicated a load of moisture. The phosphorus indicated the use of a phosphate. So the most likely problem here was that whoever was trying to clean these stamps was using a phosphate detergent. So where does the phosphorus come from? We were pretty sure that it would be a phosphate detergent. And here you can see how phosphorus is actually advertised to remove spotting and filming and to remove food and grease. And this type of phosphate, which is free of perfumes and clear of dyes, might have been used to clean the Perkins-Bacon stamp, but obviously it left a deposit of phosphate behind. But using a ×10 or ×20 a magnifying glass, you might not see this at all. When we went to the De La Rue triangle, there was no phosphate deposit, but then we were able to look at the stamp itself, and then we discovered very high levels of lead. Now, that was the age of typesetting. So basically, the workers in these printing shops were dealing with a lot of lead. They were probably remelting type and pouring new type, and this contamination got onto the stamps. Now, it's interesting, Alan Stevenson's book on Cape Triangles said and referenced that Perkins-Bacon added cyanide to their stamps because if anybody tried to clean the stamp to remove the franking, it would damage the stamp and it made the print what they call fugitive. So the way we detect cyanide is not with a scanning electron microscope, but we go to infrared spectroscopy. And we all know about the infrared and the ultraviolet, the visible light area. And what is done is a prism is used and normal sunlight is broken down into infrared. And this part is taken and used in an infrared microscope. And what is so interesting is the cyanide structure has these very strong bonds. And the infrared light comes through, but only partly, and part of it is actually absorbed. And so it's possible to look at a scan and see the effect of the cyanide bond. And it is absorbed at a very specific wavelength. So this was a reference spectrum. Prussian blue is basically a ferricyanide. And here we can see the wavelength at which the absorption takes place. We then looked at Perkins-Bacon, and sure enough, here is the same wavelength, showing that they used cyanide on their stamps. But when we went to De La Rue, there was no sign of cyanide. And we went to the wood blocks that were done in the Cape, and again, no sign of cyanide. So the use of infrared is incredibly powerful for looking at the molecular structure of materials. So I had a problem. I had bought some fairly expensive Cape triangular stamps, and one of them had stuck to the sheath in which it was placed. And my concern was that the acetate had actually become entrained in the stamp, and now the stamp had been badly damaged. This is what the back of a protected sleeve looks like. This is essentially an acetate. And the front, which is clear, has a polystyrene window. So we looked at the backing, and sure enough, it had the typical scan of an acetate. And if you look at the red, that is actually the actual pattern of the standard. And the blue is the actual acetate we analyzed. And then here is the sleeve. And the window also showed a typical polystyrene pattern. So now when we need to look at the stamp itself and this dark area, I thought I would start seeing acetate and polyvinyl and polystyrene. But interestingly, all we saw was the blue scan of standard cellulose lignin. And here you can see it. And you can see that the standard and the stamp itself are very similar. So the bottom line here was that the stamp itself was not affected by the sleeve. And there was some indication that the stamp itself, the lignin itself had oxidized and had suffered some thermal exposure, but that's acceptable if you think that it's been around for over 100 years. But this gives you an idea of some of the techniques we have used to study stamps, and I hope this has been of some interest to the audience. Thank you.